This is Health Call Online, the place for extended versions of interviews you hear on our weekly radio broadcast, the Health Call Radio Hour. Dementia and Alzheimer is a big concern for all of us as we age. Early detection helps, but that's very difficult to do. Well, now some researchers at the University of Alberta in Canada have brought forward machine learning, sort of artificial intelligence, to help with that task by analyzing speech. Let's learn more about that, talking to Zahra Shah. She's a graduate student who was involved in this research project. This is all very interesting to me, so sum it up for us. Tell me what your research found about the ability to spot dementia early just by listening to someone talk.
Yeah, so it's very interesting. Speech can be used as kind of a window into the mind, so to speak. We were able to use a few features that we computed from speech samples that were given to us. We were actually given a training set of spontaneous speech of individuals, both that were diagnosed with dementia as well as healthy controls. And these people were actually describing a picture. They were given this picture description task. So we have like 2.5 minute audio clips from each of these individuals. And we were also provided the labels telling us which are dementia patients and which are healthy controls. So what we did in our study was that we looked at three different distinct feature sets that we computed from these speech samples. The first feature set that we used was to identify the distribution of pauses within each speech sample. And so the idea here is that, so our hypothesis was that dementia patients would demonstrate longer pause durations.
So sort of while they're searching for the next word or how to carry that thought forward, they might stretch out those pauses a little bit.
That's right. So their recall is potentially not as developed as healthy controls, and so that would show up in the pause distributions within these speech samples. A second feature set that we used was speech complexity. And for this, we used, as a proxy, we used the word durations. So what we did in this particular research, we only had the speech samples and we were not given transcripts of these samples. And so we used the OpenAI Whisper ASR model, automatic speech recognition model, for developing our transcripts. And from these transcripts, we were able to look at the word distributions, and each word. So the idea was to see how long each word is spoken for, and that would be a proxy for the complexity of that word. And so if a longer word is spoken, we assume that it's a more complex word as opposed to the shorter words. And so the idea here is, again, that for dementia patients, we would expect the word durations to be smaller compared to healthy controls. That was our second feature set. And then the third feature set was of speech intelligibility. So again, we used the ASR transcripts, and we looked at the word confidence scores for each word that is generated by the model. And the idea here is to capture how well the model is able to, the ASR model is able to identify each word that is spoken. And the idea being that dementia patients might have more slurring or stuttering within their speech. And so the ASR model will have lower confidence scores compared to healthy controls.
Okay, so you look at it, you had all these samples and ran it through your algorithm. How accurate were you in being able to define those patients who had already been diagnosed with dementia?
So within our training set, we used what is known as a five-fold cross-validation. That's a kind of method of identifying within the training set how well our model is doing. And so our five-fold cross-validation accuracy was roughly 75%. But here I'd like to point out another thing within this research, which was interesting, was that the training set that we were given was from English speech samples, but the test set was supposed to be from Greek speech samples. So that's why we looked for features that could be transferred across these different languages, and so that was a pretty challenging and interesting part of this research as well.
It doesn't matter what language, when you feed the machine, the computers, with this data, all those same pauses, the way they use words, all those things, it's across all languages?
That is what was incredible to us as well. So, within so like I said, the accuracy we found within our training set, which was purely English, was 75%. When we tested on the Greek test set, it dropped down to 70%, roughly 70%. But still, I mean, given that it was a completely different language and we did not have access to the transcripts as well. We were only looking at these features that we derived from the speech samples. It was better than we all expected.
That is remarkable. Okay, so now you've got a model that can detect symptoms of dementia, I'm assuming very early in life. Where does it go from here? How might this be used?
So there's a plethora of applications that you can think of. I mean, thinking about speech as so readily available now within smartphone applications. You can imagine how it can be used. This particular technology can be used for monitoring somebody's progression as a dementia patient. This is something that really excites us because we think about how expensive at the moment Alzheimer's dementia detection is. You think about brain imaging. You consider clinical, like long face-to-face clinical interviews that happen that go in the diagnosis of dementia. And thinking of dementia as a degenerative disease, you would expect that there would be, regular monitoring, and that would be useful in this particular scenario. Given also the fact that, there's dementia is on the rise globally, we can think of deploying this technology at scale, and so there are many geographical low resource countries that are that cannot get these kind of mental health services, and so there's any number of potential applications you can think of.
Yeah, that's pretty amazing. So a smartphone app, I record a few minutes of speech and it comes back with a score as to how likely it is that I might have dementia. Not a conclusive diagnosis, but an early warning sign, right?
That's right. So that's what we keep on talking about, is that this is, we think of this more as a supportive tool rather than as a standalone diagnostic tool. That is something important to consider because we're not trying to replace the clinician here. There is very much the need of a clinician to do follow-up exams. But at the very first point of care triaging sort of thing, this speech analysis would be very beneficial.
Amazing. So let me screw on my tinfoil hat here and be a little concerned about this technology. So technically it's possible, for example, that Alexa could be listening and say, oh, by the way, you might be on path to a problem, right?
I mean, for sure, there are two sides to every coin, right? So you think about privacy issues, ethics issues. These things do come up with whenever we talk about these kind of technologies. But I think of the genie as being out of the bottle anyway by now. It's not really something that can be prevented. It's definitely something that should be regulated for sure. And in fact, I think about the fact that these technologies are so rapidly evolving is all the more reason for greater awareness and greater research within these areas. And given that we're trying to do develop these technologies for the social good. I mean, I think that's something that we all need to be aware of.
Yeah, it's amazing. When you let your imagination go, I could imagine, analyzing a cockpit voice recorder in a jetliner to monitor for the mental or the cognitive health of the pilots, for example, or how about this one? Politicians. There can be a little flag that pops up when a politician, the speeches they're giving on TV or something. That's really kind of scary, but also interesting at the same time. So, what's next? Where are you headed next with this?
So the thing right now with psychiatric disorders and computational psychiatry is that we are limited again by the size of our data sets. There is such a large array of psychiatric disorders that speech analysis could be potentially beneficial for. However, the data sets that we have, that machine learning models are based on typically, they are not as well developed as we would like for them to be. And so we're hoping that in the years to come, there will be more efforts in developing data sets like the ones we were able to access and use for this particular study to have a lot more data to work with.
So let me see if I've got this right. It's possible that down the road I could be asked to describe a picture, something I'm seeing, and you could do some analysis for not only dementia, but also depression, anxiety, all of those conditions as well, psychosis, all of that stuff you think is possible?
Absolutely. So I'm part of the computational psychiatry group here at the U Alberta. We have been looking at a variety of different psychiatric disorders within our group that includes PTSD, that includes depression, anxiety, schizophrenia, and several others. And so there's a lot of potential for speech to be used in this particular manner. Again, with the psychiatric disorders, the challenge is that all these disorders, many of these disorders, there are many comorbidities within them, and so many times even within clinical diagnoses, you can't really very easily distinguish between someone who has PTSD versus someone who has depression. So there's a lot of overlap between these diagnoses. That makes it a lot more challenging to look at. However, if we think of, just thinking of somebody's mental health in general, we can, issue alarm bells using this technology and also do something like longitudinal monitoring over time to see whether somebody's condition is improving or worsening over time. So there's a lot of potential there as well.
Amazing. So how soon before are you ready for prime time if an app could actually be in a clinic in use?
So the thing with our study here, like I said, we are limited by the size of our data sets, and so I cannot imagine clinical use of this technology anytime soon until we have larger data sets to work with and to test our models on. You would need to go through, a lot of FDA approvals, etc., and ethics regulations and those things, given that speech is such, and because we're using features from speech that are not really identifiable by humans, for example.
Oh, so I can't hear those delays. It's listening for things that I can't physically hear. That's
right. There are many things within the acoustic signal also that we use, things like pitch and how, like monotony of speech, etc. That wouldn't be that we won't be able to hear ourselves. So that's all interesting.
It's a fascinating world. Computational psychology. Is that what you said? Computational psychology?
Psychiatry.
Computational psychiatry. What other strategies, techniques, capabilities fall underneath that umbrella? I've never heard of computational psychiatry.
So what we are trying to do within our group are several things. So we look at diagnosis as well of each of these different psychiatric disorders. Like I mentioned, we've done studies on PTSD, depression, anxiety, bipolar disorder, dementia, as well as schizophrenia, and several others. But besides that, we also look at response to treatment, which means that we have things like we have data sets that my colleagues have been using on regularly, where we look at trying to see the response each individual would have to different treatments, and see who responds better.
So, are you telling me that the patient saying, yes, I think this drug is helping, or no, I don't think that therapy is helping, these computational strategies, putting the computers to work, analyzing speech or other factors, would be a more objective measurement of that? Well, you say it's not helping, but we see here that there is improvement, or vice versa.
Mm-hmm. That's exactly right. So we could look at their test scores. So, for example, if you have a clinical assessment tool, which is like a clinical questionnaire that that the subjects take before a certain treatment, and then that test is taken a few months after that treatment was imparted, and you can just see the difference between those scores and just try to predict which patients would improve and which patients would not improve.
So that happens now with the Hamilton D, for example, test is a well-accepted generalized test for symptoms of depression. And this could be an add-on to that. So here's the HAM-D score. Here's what we're seeing in this computational version. That is fascinating. Wow. What's your wild, big blue sky idea here? Where could this go? What could be the breakthrough?
So, so what excites me the most about this is how scalable this can be, given that everyone has a smartphone in their hands, and you can, so speech in particular, the other studies that I'm talking about are not necessarily speech related. So we're doing other things besides speech as well. But I have been personally involved with speech a lot more. And so speech seems to be a great biomarker that is so readily available. And again, thinking about how you could scale this up to be readily available across different countries, low resource countries that don't have access, and also within North America, you have. We're in Canada right now. If you go up north, a little farther up north, you don't have a lot of access to mental health care, for example, or other kinds of health care as well. And so just having a smartphone be able to monitor our health, that sounds really exciting to me.
It's fascinating. Speech as a window to the mind, thanks to artificial intelligence and computer learning. That's fascinating. Sarah Shah, thank you so much for joining us and telling us about it.
Absolutely. Thank you for having me, Lee.